Hello, so today I'm going to explain what tension is because it can be tricky to understand, and I'd like to clear up any potential confusion about this physics concept. So often tension is explained as follows. So let's say we draw this plane or surface, and let's say there is a hinge, then there is a rope hanging off this hinge, and let's say on this rope is a certain mass that's hanging off the rope. And people often say, well, mass, it's pulling down with a force of mg, and therefore there's a force of tension upwards, Ft. And this might be a little confusing. Why is there tension upwards? Why is the rope not being pulled downwards along with the mass? Since the mass is pulling downwards, why is the rope also not downwards? Why is there no such, tension downwards? Why is there no such thing? Well, technically there are two ways to visualize this. So the first way is where indeed you would see the rope being pulled downwards. So if you take this mass, the mass pulls down of mg, and you might actually think that the rope is getting pulled down with the mass, therefore it's going like this. And in this hinge, let's just magnify it. So I'm going to magnify it in this bubble right here. Let's say we have this hinge, and since the rope is pulling down on it, the hinge will be pulling up on the rope. That's one way of seeing it, but the way you see it in physics class is like this. This is the way that is the proper way to see tension. So there's no force downwards. Instead, what happens is you have this hinge, and you have the rope pulling downwards, and we have the mass right here. It's pulling down with a force of mg. And the rope, if we magnify this portion right here, what's happening is that there's this rope, and then there's the start of the mass right here, and the mass is pulling downwards. So in order to prevent the mass from falling, the rope has to pull upwards, and that is Ft, force of tension. So you wouldn't visualize it using the first way. So you wouldn't visualize it this way. You would visualize it this way, where the force of tension is upwards on the mass and therefore prevents the mass from falling down. The rope pulls up on the mass to prevent it from falling down. Don't imagine it as if somebody's actually tugging on the rope. Nothing's being actually moved here. It's just this rope prevents the mass from falling down. Therefore, the rope exerts a force of tension upwards on the mass to prevent it from falling down. This is how you would imagine tension. So let's say it's tension can get a lot trickier. So let's get into pulleys. So let's say we have this cliff right here. We have this pulley attached right here. It's like a little wheel attached right here, and there's a rope passing over it. So we have this M1 right here, and M2 right here. And how do we exactly visualize the tension in this case? So what tension is, it's the force that the rope applies to resist something. So let's say, since M2 is exerting a force downwards, mg, well, m2g, this system is going to move downwards, entirely downwards. And how do we exactly understand the tensions in the rope? So because this M1 is going to be dragged with a force of m1a. It's going to be dragged in this direction. M1 also resists it with a force of m1a. It doesn't want to go forward because it has this inertial tendency to resist the motion forward. So to prevent m1a from resisting, the rope has to drag it with a force of m1a. So m1a in this case right here, that's just the inertial tendency. That's the inertial tendency of the object not to accelerate. And the rope therefore has to exert a force of m1a on it for m1 to move forward. So m1a will be tension in this case. So Ft points this way. The force of tension that the rope has to exert to move m1 points that way. But what about for m2? What happens? Well, if you think about it, m2 is, had there not been m1, if the m1 wasn't attached right here, m2 would actually accelerate downwards with the gravitational acceleration. It would be in free fall. Nothing is pulling it backwards. But in this case, because m2, while having to fall downwards, is also tied to this heavy mass right here, it's going to be slowed down. Its acceleration is not going to be as fast downwards because this m1 is technically pulling it backwards. So what happens is that tension of the rope in m2 prevents it from fully accelerating downwards. So there's going to be a tension upwards, Ft. And tension is going to be the same magnitude as this tension right here. So this tension and this tension are the same because keep in mind that this rope is continuous. If we were to, let's say, instead, we were to draw this system, let's say we had not a pulley, but we had this thing where it would pinch the rope off. So there would be part of the rope going this way, part of the rope going this way, and this rope is stationary. It's not mobile. It cannot shift over. And let's say this M is right here, and this M is right here. The force of tension in this case, in this side of the rope, would be 0 because it's not moving anywhere. It's just this mass. This mass is stationary right here. It's not moving anywhere, and just rope is simply attached to this area. It's not a pulley. Then Ft would be 0, and in this case Ft would equal mg because it's just simply this mass pulling down on the rope and just hanging off the rope, and the rope has to exert the tension upwards on it in order to prevent this mass from falling, Ft. So this situation is quite different from this situation where the rope is actually continuous and it moves entirely with the masses. So in this case, since m1 resists the pull of the rope on it, the tension points this way because the rope exerts a tension of m1a on it to resist its inertial tendency to remain still. And in this case, the rope actually slows down the acceleration of mass 2 downwards because keep in mind that there's this big mass tied right here. So the force of tension is going to be upwards in this case because the rope is slowing down the acceleration downwards. It's going to be a force of Ft that is equal to Ft right here. You may ask why? Well, because keep in mind that tension is transferred throughout the rope, this force of tension. And in this case, m1 is being accelerated, and this affects the tension right here too. In the next video, I'll actually discuss pulleys, where it becomes more apparent how tension is transferred throughout the rope. But hopefully for now, this at least will help you visualize what tension is. And another way to imagine tension is, let's say we just draw the ceiling right here. and we draw the rope and the mass right here. And we can imagine the rope as follows. So M pulls down with mg on the rope, and therefore you can say that this part of the rope pulls up with a force of mg to prevent M from falling. And we can also say that this entire part of the rope, because it's pulling up on mg, it's also pulling down this part of the rope, this higher part of the rope, which also has to exert a force of mg to pull up, this part of the rope. So the tension gets transferred throughout the rope. Each part of the rope has to support the other part from falling down. So each part of the rope has to exert a force of tension upwards. Therefore, that's how we envision the force within the rope, as a tension upwards that prevents the mass from falling downwards. And we could clearly see it in this case, where to get this M1 moving, the force of tension has to pull it in a certain direction, otherwise M1 would not be moving. So force of tension in the rope has to pull it one way, and in this case the force of tension actually pulls this M2 upwards, but not enough, because M2 is still accelerating downwards, but it's accelerating slower, because keep in mind that the rope connects both of them, and because of that there's this M1 right here that's getting dragged, and it's slowing down the acceleration of M2 downwards. Therefore, the force of tension in this case, it's upwards. And you can just visualize it even without these fancy diagrams. Just portray it accelerating in your mind, and you'll see that M2 clearly, you can imagine, will not accelerate as fast as it can because of this heavy mass tied right here. And then you can clearly imagine in that case that means that the rope slows down M2 from fully just falling downwards. Therefore, where's the tension in the rope? Upwards. And in this case, you can clearly imagine M2, the M2 g-force getting transferred throughout the rope, pulling this M1 down. But in order to pull it down, it has to pull down with a certain tension, because it doesn't pull down with a tension of M2g. Instead, it pulls down with the necessary force to accelerate this object to whatever this whole system is accelerating with. So in this case, it's going to be M1a. Because keep in mind that M2g, yes, there is a force of M2g, but this force is not going to get fully exerted on M1 because the system is accelerating at a different acceleration from g. And that's because also you can imagine that M2, since it's getting partially pulled upwards, the net force on the rope, therefore on M1, is not going to be the full M2g downwards. It's going to be M2g, it's not going to be that full M2g. Instead, it's going to be M1a in this case. That's the force on M1 that is required to pull M1. So that's why this M2g force does not get fully transferred in here. Instead, it's a different force that's pulling on M1 in order to get it moving. And meanwhile, M2 in this case actually accelerates with a force of M2a. It's that's the net, force on it that's pulling it down. So Ft in this case is equal to M1a, and that's how you can understand the tension in this situation.